Color perception. Electromagnetic radiation. Light is a form of electromagnetic radiation. And electromagnetic radiation is all around us, moving through our bodies, filling the air. To understand what electromagnetic radiation is to understand waves. A wave has both a wavelength, which determines its color, and an amplitude, which determines its brightness. Also, electromagnetic waves move as transverse waves, which is similar to how a string waves when it's plucked. Light is one tiny portion of the electromagnetic spectrum. The spectrum refers to the entire range of wavelengths, with radio waves being as long as 2 football fields, and with gamma rays with wavelengths too small to measure, being the thickness of atomic nuclei. Microwaves happen to be a wavelength that closely matches water molecules, and because of this, sets the molecules to jostle, and the movement of those water molecules create heat. The visible spectrum sits somewhere in between, with wavelengths from about 380 to 740 nanometers. A nanometer is 1/1000th of 1 meter, a meter being slightly longer than a yard. And it's within this narrow range of wavelengths that the electromagnetic waves enter our eyes and interact with our physiology. The shorter of the visible wavelengths, about 400, are violet, and the longest of the visible wavelengths, around 700 to 740, are deep red. In the middle are greenish wavelengths. White is perceived when there is an equal combination of visible wavelengths. If white light is passed through a glass prism or a droplet of water, the density of the glass will bend the light corresponding with its wavelength, splitting it into wavelengths from long to short. In a vacuum, light travels at almost 200,000 miles per second, which is incomprehensibly fast. Light moves slightly slower in denser materials, like water, and that's why they bend. Spectrophotometers. They're instruments used in graphic communications called spectrophotometers, and these measure the relative intensity of a light source across the visible spectrum from 380 to about 740. Here, you see the green and the lime colors being dominant in the color that's being measured. These devices were at one time prohibitively expensive, but today a good spectrophotometer can be purchased for under $2,000. Here's an example of white light sources. Note that none of these white light sources are balanced in intensity across the entire visible spectrum. Again, there's no such thing as true white. Rather, white is interpreted by the brain. We'll talk more about white light sources when we discuss color temperature. Keep in mind, there is no color without you to perceive it. Color is actually a physiological response to electromagnetic radiation in the environment. This is an illustration of the human eye. Light passes through the cornea, which is a protective layer over the lens. The iris opens and closes to control the amount of light that enters the eye, and the lens focuses the light onto the retina. The retina is made up of specialized cells, and these cells are in the shape of rods and cones. The rod-shaped cells can't discriminate wavelength, but can discriminate amplitude or brightness. These cells respond to value or shades. The cone cells respond to specific wavelengths of light, and thus are responsible for our perception of color. There are 3 types of cone cells. We have blue cones, sensitive to the 420 to 440 nanometer segment of the visible spectrum. We have green cones, sensitive to the 534 to 545 nanometer segment, about in the middle. And we have red cone cells, which are sensitive to the 564 to 580 nanometer segment. So in actuality, our retina contains the ability to only see 3 colors: red, green, and blue. To understand how the brain interprets combinations of these red, green, and blue stimulants. Note on the left the cone subtype that is stimulated by that wavelength of light, and on the right, the color perceived by the brain. Let's look at yellow. When the red cone cell and the green cone cell are stimulated, but there's a lack of wavelengths in the blue segment, our brain perceives the color yellow. Look at white. When red, green, and blue are all stimulated simultaneously, we have the perception of white. A little bit more about the retina. It's important to note that the cone cells are not evenly distributed throughout the retina. The outer retina contains the greatest concentration of rods, and the macula, which sits straight behind the lens, contains the greatest concentration of cone cells, and the fovea represents the area of highest focus. Also, the distribution of cones, or the number of cone cells, are not evenly distributed at the macula. We have a high percentage of red cone cells in the macula, fewer green cone cells, and very few blue cone cells. But note here, where we have blue text over gray, how difficult it is to read. And that's because we have relatively low color acuity to blue, whereas red is easy to read over the gray because we have much higher color acuity at yellow, red, and orange. About 1 in 10 people have some degree of color deficiency, at one time called color blindness. Most often, this is red-green cone confusion. And tests like this color deficiency test, which by the way is not official because its brightness and saturation is not exact, but this will give you an idea. So in the upper left corner, if you can't read 25, you're most certainly color deficient. The hardest ones to read are the upper right 6 and the left middle 45. So the term color acuity refers to the ability to distinguish very slight color differences. And humans vary in this ability quite substantially. As we age, our lenses fog in yellow, and so our color acuity drops. Also, the fluid between the lens and the retina, called the vitreous humor, absorbs more light, and so we need more light to see well. This shows a light level test, where older people would have much more trouble distinguishing the colors and numbers on the right. To test color acuity, an official test is called the Farnsworth-Munsell 100 hue test. There are 2 variations of this. One, which we have in our lab, is where physical caps are placed in order within a certain period of time, and then software is used to interpret that into a color acuity score. There's also an online version of this, which is not as accurate. The Farnsworth-Munsell hue test has shown that on average, women have better color acuity than men, young people better color acuity than older people. But there are wide variations within the population. Here are some color effects that show how the brain interprets color based on the surrounding color. The brown color on the left is same as the brown color on the right. However, they'll look different side by side because of the yellow and blue surrounds. To assure that this doesn't affect color proofing in the graphic communications industry, we have color viewing booths, and we also have viewing standards called color temperature on our displays. Here's another example of adjacent color effect. On the right, the blue looks darker than on the left. However, these colors are identical. Further, the length of time we look at a color will affect its color intensity. If you stare at the black dot in the middle of these color squares for a few seconds, and then look away at a white background, you'll see a color reversal. That is, red will become cyan, yellow will become blue, blue will become yellow, and green will become magenta. This has to do with the cones decreasing in sensitivity as they are stimulated. Looking away at white illustrates the cones that have been affected. Similarly, the brain will create color adjacency effects. This is called the reversal effect. And if you stare for a few seconds at the green dots and then look at the white square adjacent, the colors will reverse themselves. This is purely happening in your brain.